Hi, I'm Gianluca, and welcome to this deep dive into one of the most important ideas in statistics and data science, the normal distribution, also known as the bell curve. You've probably seen this shape before, even if you didn't realize it. It shows up when we analyze natural phenomena like human height or biological traits. It appears in exam scores and standardized tests. It's used constantly in finance to model returns and risk. And it's built into many machine learning models to describe noise, errors, and uncertainty. In this video, you'll learn what the normal distribution is, how to interpret its key parameters, the mean and standard deviation, and how to use tools like the 68, 95, 99, 7 rule and z-scores to answer real probability questions. We'll also see why this curve appears so often in the real world and how it powers applications from risk management to modern AI. Let's get started. On this slide, I want to give you an intuitive feel for where the bell curve comes from. Imagine we start on the left, each dot is one outcome, a person's height, an exam score, or a small measurement error. At first, they just look like random noise scattered along a line, with no clear structure. Now, as we move toward the center of the slide, we begin to see a pattern. The dots cluster more densely around the middle and thin out toward the sides. A smooth outline starts to emerge behind them. On the right, that outline becomes a clean bell-shaped curve. This is the normal distribution. The key idea is this. When many small, independent random influences add up, genetics, nutrition, study habits, tiny instrument imperfections, their combined effect tends to follow this bell shape. Values near the center are very common. Average heights, average exam scores, errors close to zero. Extreme values, very tall or very short people, very low or very high scores, huge measurement errors are much rarer, sitting out in the thin tails of the curve. Now that we've seen the bell curve intuitively, let's define it more formally. What you're looking at is the normal distribution. It's a continuous probability distribution, and its shape is completely determined by just two numbers, the mean, written as mu, and the standard deviation, written as sigma. Along the horizontal axis, we have the possible values of our variable. Along the vertical axis, we have probability density, which tells us how likely values are to occur in different regions. The mean mu is the center of the distribution, the peak of the curve sits right above it. The normal distribution is perfectly symmetric around this mean. That means values that are 1 unit below the mean are just as likely as values 1 unit above it. The standard deviation, sigma, controls how spread out the curve is, but we'll explore that in more detail on the next slide. In the formula you see on the right, changing mu shifts the curve left or right, and changing sigma stretches or compresses it, while preserving this characteristic bell shape and symmetry. On this slide, we are going to make the ideas of mean and standard deviation very concrete. Start with the vertical line at the center of the bell curve, labeled mum mean. This is the average value of your data, and it represents the balance point or center of the distribution. If you took all your observations and averaged them, you'd land right at this line. Now look at the brackets for plus or minus 1 sigma, 2 sigma, and 3 sigma. Sigma, the standard deviation, measures how spread out data are around the mean. If most of the curve's area is squeezed tightly near mu, sigma is small, values are clustered close to the average, and the curve looks tall and narrow. If the curve is flatter and stretches far to the left and right, sigma is larger, values are more dispersed, and there is more variability. The small comparison curves in the corner reinforce this. A narrow bell curve corresponds to low variability, while a wide bell curve corresponds to high variability, even if they share the same mean. This slide shows one of the most useful shortcuts for working with the normal distribution, the 68, 95, 99.7 rule. Because the normal curve is fully determined by its mean mu and its standard deviation sigma, we can say how much of the data typically falls in fixed bands around the mean. In any normal distribution, about 68% of all values lie within one standard deviation of the mean between mu minus sigma and mu plus sigma. If we widen the interval to two standard deviations from mu minus 2 sigma to mu plus 2 sigma, we capture about 95% of all values, and if we go out to 3 standard deviations on each side, mu plus or minus 3 sigma, we include about 99.7% of all values. For a concrete example, imagine adult male height is approximately normal with a mean of 175 centimeters and a standard deviation of 7 centimeters. Then roughly 68% of men are between 168 and 182 centimeters. 95% are between 161 and 189, and only about 0.3% are shorter than 154 or taller than 196 centimeters. Now that we understand the shape of the normal curve, let's see how to answer probability questions with it using z-scores. Suppose height is normally distributed with mean mu and standard deviation sigma, and we want to know what fraction of people are taller than 190 centimeters. First, we standardize 190 into a z-score using the formula in the box z equals x minus mu divided by sigma. This z-score tells us how many standard deviations 190 is above the mean. For example, if mu is 175 and sigma is 7, then z is about 2.1, meaning 190 is roughly 2.1 standard deviations above average. Once we have z, we move from the original height scale to the standard normal scale, where the mean is 0 and the standard deviation is 1. Then we can look up the area to the right of that z-score in a standard normal table, or compute it in software. That shaded right tail on the slide represents exactly this probability, the fraction of people exceeding our chosen threshold. Now let's answer the question, why does this bell curve appear so often? This is where the Central Limit Theorem comes in. Look at the left panel. Our original data can have many different shapes. It might be uniform, strongly skewed, or even have two peaks. None of these looks like a bell curve. Now move to the middle panel. Imagine repeatedly drawing random samples from each of these distributions, and for every sample you compute its average or sample mean. Each dot or small tick there represents one of those means. As we collect more and more sample means, something remarkable happens, shown in the right panel. The histogram of these means starts to look more and more like a bell curve, regardless of the original shape on the left. The Central Limit Theorem says when you add or average many independent random effects, the distribution of their sum or their mean tends to become approximately normal. This is one of the main reasons the normal distribution shows up everywhere in real data. Here you can see how the normal distribution shows up in very different real-world settings. On the left, think about human height. If you measure a large group of adults, most people cluster around an average height, with fewer very short and very tall individuals. A bell curve fits this pattern extremely well, and lets us answer questions like what proportion of people are taller than 190 centimeters, or how tall is someone in the top 10%. In the center, standardized test scores and IQ scores are deliberately designed to follow an approximate normal distribution. That makes it easy to define thresholds, the top 2%, the bottom 5%, or one standard deviation above average. On the right, consider measurement errors from instruments like scales and thermometers. Each reading is affected by many tiny independent imperfections. Those small effects add up to errors that are usually close to zero and symmetrically distributed, again well modeled by a normal curve. In all these cases, the normal distribution helps us predict frequencies, compare individuals, and set meaningful cutoffs. On this slide, we are looking at two major application areas for the normal distribution: finance on the left and machine learning on the right. In finance, daily or weekly returns are often modeled as approximately normal. The histogram of returns can be overlaid with a bell curve to estimate how likely different gains or losses are. This underpins many risk measures. For example, value at risk assumes a distribution of returns to quantify how large a loss we might exceed only, say, 1% of the time. However, real markets have fat tails and extreme events occur more often than a perfect normal model would predict, so this assumption must be used with caution. On the machine learning side, many models assume that errors and noise are Gaussian. In linear regression, for instance, we often assume residuals follow a normal distribution centered at zero, which justifies least squares estimation and classical confidence intervals. More broadly, Gaussian noise is built into probabilistic models, Kalman filters, and many neural network methods, influencing how we model uncertainty and optimize loss functions. In this video, you've seen why the normal distribution is a cornerstone of statistics and data science, a simple bell-shaped curve fully described by its mean and standard deviation that lets us quantify uncertainty with tools like the 68-95-99, 7 rule, z-scores, and the Central Limit Theorem. Because so many real-world phenomena and aggregated effects are approximately normal, this single model underpins applications from education and measurement to finance and machine learning. To really understand these ideas, you need to practice them. That's why I created Statistics with Python, 100 solve exercises for data analysis. Inside, you'll find step-by-step Python exercises on probability, hypothesis testing, correlation, regression, and broader statistical analysis, all written to help you move from theory to working code and real insights. If you'd like to deepen your skills, check out the book and start coding through the exercises in Python. Thank you for watching. If you found this helpful, please like the video, subscribe to the channel, and leave a comment with any questions or topics you'd like to see next.